Okay, so we're going to have a look at this differential equation from 2012. So we're told in the question that a particle of mass m is fired horizontally through a block of resistive gel. So we're just going to draw a sketch of what we think this looks like. So this is the gel here, and we know that the speed of the particle as it enters the gel is 1000 meters per second, and then it exits the gel with a speed of 10 meters per second. So we can see that the particle is obviously decelerated as it's passed through the gel. We're told that there is a resistance to motion of mkv squared. So we have a force here acting in the opposite direction to motion. So the force is equal to minus mkv squared. So obviously the force, this resistance, is some proportion of the velocity squared. So we know that F is equal to mass times acceleration, so we can say that the mass times the acceleration is equal to minus mkv squared, and then we can divide both sides by m to give us that A is equal to minus kv squared. So the acceleration of the particle through the resistive gel is minus kv squared, so it's some proportion again of its velocity squared. We're told that the time taken to pass through the block is 1 over 100 seconds. So what we can do is we can say that the time entering the block was 0 and the time exiting the block is 1 over 100. So we can now use these times and their corresponding velocities to calculate the value of k, which is what they ask us to do in the first part of the question. So let's just run through that initial part quickly again. We know that F is equal to ma. The force in this question is only acting in the opposite direction to motion, so minus mkv squared is equal to ma. We're going to divide both sides by m to give us that the acceleration is minus kv squared. Because I have limits for time and velocity, I can change acceleration into dv dt. Remember that acceleration is the change in velocity over the change in time. So dv dt is equal to minus kv squared. I'm going to collect the v's on the left hand side and the t's on the right hand side. So I divide both sides by v squared to give me 1 over v squared. dv is equal to minus k dt. And I'm going to integrate both sides of this differential equation using the following limits. When the time was 0, we know that the velocity was 1000. And then 1 over 100 seconds later, when the time was 1 over 100, we know that the velocity had reduced to 10 meters per second. Integrating the left-hand side with respect to v, I know that 1 over v squared is the same as v to the power of minus 2. So if I raise the power, minus 2 turns into minus 1, divided by the new power minus 1. And if we integrate the right-hand side with respect to t, we get minus kt. V to the power of minus 1 over minus 1, I am just going to rewrite as minus 1 over v. And then I'm going to sub in the limits. On the left, 10 and 1000, and on the right, 1 over 100 and 0. A tenth minus 1000 is 99 over 1000, and that's equal to k over 100. And if I multiply both sides by 100, I get k is equal to 99 over 10. We were asked to show that in the first part of the question, and we've now shown that k is equal to this value. So we can now use this value of k to update our acceleration. Our acceleration was minus kv squared, and we can now write this as minus 99 over 10 v squared. Part 2 of the question asks us to show that the length of the block is 10 over 99, the natural log of 100. So we're asked to find the length of this block. So if I use the letter s for displacement, I can say that s is equal to 0 when the particle enters the block, and we're looking to find the value of s as it exits the block. So we have a formula for acceleration, which is minus kv squared, and we know that we can change acceleration into dv dt, which is the change in velocity over time, or we can change acceleration into v dv ds. We haven't got a formula that can work with s's and t's at present, so what we're going to do, instead of finding the distance traveled from the time is 0 to the time is 1 over 100, we're going to find the distance traveled from when the velocity was 1000 to when the velocity was 10, and that allows us to use this formula for acceleration. So we'll start with that. So v dv ds is equal to minus kv squared. We're going to collect the v terms on the left and the s terms on the right. So dividing both sides by v squared, we get 1 over v dv is equal to minus k ds. Remember that we found the value of k to be 99 over 10, so we can sub that in as well before we start the question. So we're going to integrate both sides and we're going to use the following limits. We know that the displacement or the distance travelled by the particle on entering the block was obviously 0, and this occurred when the velocity was 1000. And we're looking for s, the displacement or the distance travelled, when the velocity had decelerated to a speed of 10 meters per second. So integrating 1 over v with respect to v, we get the natural log of v, and integrating minus 99 over 10 with respect to s, we get minus 99 over 10s. Subbing in the limits on the left, 10 and 1000, and the limits on the right, s and 0, we get that the log of 10 minus the log of 1000 is equal to minus 99 over 10s. I'm going to collect the s's on the left to give me 99 over 10s is equal to log 1000 minus the log of 10. The rule of logs tells us that the log of a minus the log of b is equal to the log of a over b. So 99 over 10s is equal to the log of 1000 minus the log of 10, which is the log of 100. I'm going to divide both sides by 99 over 10 to give me s is equal to 10 over 99, the natural log of 100. And so that's the distance travelled by the particle in 1/100th of a second, and it's also the length of the block, as that's how long it took for the particle to pass through the block.